You ever look at our biggest, wildest engineering dreams, fusion reactors, rockets to Mars, elevators to space, and wonder what's really holding us back? It turns out it's not always about imagination or money. More often than not, it comes down to the very stuff we have to build with. So let's really dig into that. What is the one thing, the fundamental bottleneck, that stops these incredible projects in their tracks? Well, the answer is kind of surprising. It's often something as simple as the material itself.
I mean, think about fusion power. The goal is literally to build a tiny star here on Earth. Just imagine nearly limitless clean energy. It's an absolutely incredible idea.
Or what about the space elevator? This has been a sci-fi dream for decades, right? A single cable stretching from the ground all the way up into orbit. Space travel would become as simple as hopping in an elevator. And then you've got railguns. We're talking about electromagnetic launchers that could fire projectiles at insane hypersonic speeds. I mean, this could totally revolutionize everything from warfare to launching satellites. Each one of these is a complete game changer. But, and here's the catch, every single one of these revolutionary ideas runs headfirst into a very specific and very, very difficult materials science problem. They all get stuck at the exact same point: the materials bottleneck. Okay, now this is where it gets really interesting, because you can see the pattern right here. For the fusion reactor and the space elevator, we need a miracle, a breakthrough in materials that, well, they just don't exist yet. For the railgun, it's a durability problem we just haven't cracked. But look at the one at the bottom, Starship. The materials to survive that insane 1400-degree reentry, they exist. The bottleneck isn't a new discovery, it's about integration. And because that's an engineering puzzle being solved right now, that's what we're going to focus on. So yeah, let's zoom in on the most immediate, most tangible example from that list, SpaceX's Starship. This isn't science fiction. This is a brutal engineering challenge playing out in real time with every single test flight. So the problem is something called aerothermal heating. Basically, as Starship comes screaming back into the atmosphere, it's moving so unbelievably fast that it compresses the air in front of it into a superheated plasma. It essentially turns the front of the ship into a blast furnace. And we're talking about temperatures around 1400 degrees Celsius. That's over 2500 degrees Fahrenheit. It is hot enough to melt the stainless steel that the spaceship is made of. And the most vulnerable parts of the whole vehicle, the control flaps. And this quote just says it all, doesn't it? This isn't some computer simulation or theoretical problem. This is what engineers were actually seeing in the data from the test flights. The very things you need to steer this giant rocket to a safe landing were literally being destroyed on the way down.
So what do if you're an engineer at SpaceX and your flaps are melting? You don't just pack it in and go home. You open up the playbook. And it turns out there's a whole hierarchy of solutions, from the simple, quick patches to fundamental, ground-up redesigns.
First up, you try this simple stuff, the low-cost fixes. Think of this like battlefield medicine for a rocket. You can slap on some cheap, replaceable caps on the edges, basically giving the heat something to destroy that isn't the flap itself. Or maybe you paint on some special ablative coatings that just burn away, carrying the heat with them. You can even just tweak the flight path a little to try and ease up on that peak heating. It's quick, it's dirty, but it might just get you to the next flight. Now, if those simple fixes aren't cutting it, you've got to move on to more complex changes. And this is where the real design work happens. Instead of just a cap, you design modular skin panels that you can swap out. You take the delicate motors that move the flaps and bury them deep inside the structure, connecting them with these long heat-resistant tubes. You could even embed something like heat pipes to literally wick the heat away from the hot spots and spread it out. And then, if all of that still isn't enough, you have to bring out the big guns. These are the super expensive, super complex solutions. We're talking about active cooling, literally pumping fluid through the flaps just like a radiator in a car. Or using exotic, and I mean exotic, materials like ultra-high temperature ceramics that can just laugh at that kind of heat. You could even totally reshape the flap to change the aerodynamics. These things will work, but boy, do they add weight, cost, and a whole lot of new ways for things to go wrong. So you see the problem here, right? Engineers are in this constant balancing act. A simple fix is cheap and light, but you might have to replace it after every single flight, which totally kills the dream of rapid reuse. A complex fix might be way more reliable, but it could be so heavy and expensive that it makes the whole rocket uneconomical. There's just no perfect, easy answer. And all of this, it brings us to a much bigger and honestly a more provocative question. With all of these insane challenges, what is the ultimate fate of Starship? Is it really going to be the revolution that we were all promised?
Now, this is a pretty shocking statement, I know, but it's a real conversation happening in aerospace circles. What if the Starship vehicle itself, the part that's supposed to take people to Mars, is just fundamentally flawed? And when you look at the arguments, they're pretty compelling. There's no launch abort system for the crew. That whole belly flop and flip landing is probably way too violent to ever be rated for humans. The heat shield tiles are fragile, which brings back horrible memories of the Space Shuttle Columbia. And look, if they're struggling this much with re-entry on Earth, a Mars re-entry, which is 4 to 5 times more intense, is completely out of the question. That dream of a gas-and-go rocket is starting to look a lot more like the Space Shuttle's expensive, months-long repair job. Which leaves us with this final thought to chew on. Is Starship really the ship that's going to take humanity to Mars? Or could its most realistic future be something a lot less glamorous? Maybe it's just a really powerful, semi-reusable cargo hauler, an orbital gas station, basically the world's most expensive tanker truck for other tougher spacecraft that will actually make the trip to the moon and beyond. Now, that might not be the grand vision of colonizing Mars, but hey, it could still be a revolution in its own right. What do you think?